So all questions will be answered at a point during the workshop. As Manuel already announced, I will give a presentation on causal inference using parametric structural equation models. And my goal is to make a link between causal models on the one hand side and statistical models on the other hand side. And quantitative psychologists and behavioral scientists often make use of multivariate statistical models, such as covariance structure models, or some of its special cases like confirmatory factor analysis, multi-level models, and so on and so forth. And the general question I'm asking is, can these statistical models be used for causal inference based on observational data? Or to which extent can these models be used for this purpose? Or under which assumptions can these models be used for this purpose? So the fundamental distinction I'm going to make is between statistical models and causal models. And statistical models and their parameters, they do not have a causal interpretation per se. However, there are situations in which statistical parameters can be linked to causal quantities. And one very strong argument for causal interpretation of statistical parameters is a strong design, for example, a randomized controlled trial. And then under certain assumptions, the mean differences you observe in the data, if you have such a design, can be interpreted as an average treatment effect. Today, I will focus on a different approach that does not have a strong design component, but we just basically have observational data without intervention or without experimental manipulations. And the question is, under which assumptions can results from these studies be interpreted causally? And I will make use of the graph-based approach advocated by Judea Pearl based on directed acyclic graphs. So just to give you an impression of the distinction between statistical models and causal models, statistical models basically focus on observed data and the joint distribution of observed variables. And means, variances, covariances of these observed variables are all part of the statistical models. Regression coefficients, conditional means, at the beginning, they're all part of the statistical model. On the other hand, we have causal models, and terms like potential outcomes or counterfactuals, causal effects, indirect total effects, average treatment effects, all these terms are part of causal models. For example, the Neyman-Rubin causal model, potential outcome model, or the graph-based causal model. And also these causal assumptions like ignorability, conditional ignorability, no unobserved confounding, no interference, they also belong to the realms of causal models. And then we have two candidates that have been subject to more debate, whether they are statistical or causal models. I think with Wright's path analysis, it's been clear that this is a causal model, but with structural equations, there has been more of a debate. And I think the roots, the origins of structural equations are clearly causal. However, I also think that the term SEM, structural equation modeling, has changed over time. And today, in standard textbooks about SEM, SEM is introduced as, I don't know, as a group of statistical techniques in a way. So I will use structural equations as part of causal models, but I'm aware of that the term SEM is also used to refer to a collection of statistical techniques, just to make this clear here, so we won't run into misunderstandings. And to link the causal models with the statistical models, we need something which is called causal identification. And in the research process, that aims at explanation and at causal reasoning and causal conclusions, one should start with setting up a causal model, which is a scientific task. And causal modeling requires expert understanding of the scientific subject. And it asks questions: what would happen to an outcome if one intervened or manipulated an exposure? And causal reasoning is done based on these causal models and logical thinking, and does not require statistical expertise whatsoever, because causal modeling is different from statistical modeling. Of course, after such a model has been set up, a causal model, one could decide to support, quantify, test, or falsify this model using quantitative observations and statistical techniques. But that's on a different step of the research process. And I will now give you a brief introduction of the graph-based causal model and its key assumptions. So there are 3 key assumptions, namely a priori causal knowledge needs to be there to use this framework. One needs to assume modularity, so autonomy, stability, modularity, or invariance. I've put these 4 terms here because they refer to very similar concepts. I do not claim that they refer to exactly the same concepts, but somehow they're used synonymously, and I just wanted to include them all for the reasons of completeness. But I will focus on the term modularity, and autonomy, stability, and invariance, I think, are very similar to modularity. And the third assumption is no interference, and I will walk you through these assumptions step by step. So a priori causal knowledge means that we need to have a theory about the causal structure of the data generating process that we represent with a graph. And a graph consists of nodes, here x, y, and z, which correspond to random variables. And a graph consists of edges. Here we have directed edges that have one arrowhead. These directed edges represent direct causes. So here I express my belief that x is a direct cause of y, or z is a direct cause both of x and y. And we have a second ingredient in our graphical depiction here. We have like this bidirected or undirected edges, which represent the assumption of an unobserved confounder. So this representation here basically is equivalent. It's just a shorthand notation for this situation where I assume that the relation from x to y is confounded by an unobserved variable called u, an index xy. And unobserved variables are usually displayed in this dashed ellipses. So this is the causal structure one needs to know as a priori knowledge. And after drawing a graph, this graph uniquely implies a set of non-parametric structural equations. And the rule is, for example, if we look at the equation for x, that x is a function of all its direct causes, namely z, and the unobserved cause, u, and an error term. And the error terms, that's a convention in the graph-based framework, are not depicted in the graph, but they're part of the equations, these error terms epsilon. And we need to make another assumption, namely that all the unobserved variables are mutually independent. This is the assumption denoted here. So that's our starting knowledge we need to have. And the great thing about this graph-based framework is, or one great feature is, that it's non-parametric in nature. So we do not need to make any assumptions about the functional form of these structural equations here. And yeah, so we can model very flexible relations, because basically we can model all types of relations in a non-parametric way. So what we need to know is the causal structure, but we don't need to know the type of functional relationships. And these non-parametric equations, of course, they contain the linear case as a special case. They contain moderated relationships as a special case. They are very flexible. And also, we do not need to make assumptions about the distributional family of the unobserved variables. We just need to assume that these independence relations hold. The second assumption, called modularity, means that an intervention on one variable alters the level of this particular variable, but not the relationships among other variables. So what does that mean? If we do a certain type of intervention in the system, which is called a do-type intervention, a do-type experiment. So if we have an experiment or a hypothetical experiment in which the treatment do X is uniformly applied to the entire population, and in this experiment, the treatment level of X is deliberately chosen by the experimenter. In such an experiment, the structure can be depicted like this. So what happens? The variable X is no longer determined by its direct causes, because now X is under the control of the experimenter. So that's why X has no incoming edges anymore. And the assumption of modularity basically says that all other relations in the system remain unchanged. So Z is still a direct cause of Y, U is still a direct cause of Y, and also the quantification of these relationships, the functional relationships, did not change. Because of the intervention, the only equation that got changed is the one for X, so the variable which we intervene on. That's the assumption of modularity. And the assumption of no interference maybe is a little more well known outside of the context of causal inference. And it basically means that the treatment status of one unit, maybe of one person, if we analyze persons, does not affect the treatment status or the outcome of other units. So what does that mean? That means that whether or not one person is in the treatment group does not affect the behavior or the outcome of any other person in the study. And if, for example, we in our study we include couples. So, like for example, a person is in the treatment group, but the spouse, this person's spouse, is also in the study. And then, whether or not one person is in the treatment group and the other is in the control group, they might communicate, and this might affect their behavior and this might affect their outcome. If we think that this is the case, we should draw a different graph. Namely, for example, if we believe that the treatment status of unit J, of person J, affects the outcome of another person Y, we should probably draw this kind of graph. And usually we don't do this. Usually we draw the standard graphs here, and this standard graphs excludes the possibility of interference. And causal reasoning based on graphs is then done based on the interventional distribution, which is denoted by P of Y given the intervention on X. And this distribution describes the probability, or is the probability distribution of an outcome variable Y had the treatment X been uniformly applied to the whole population, to the entire population. And we can look at certain features of this interventional distribution. We can look at the interventional mean, which is the average value of the outcome variable y one would observe in the population had the treatment do X been uniformly applied to this population. One could look at probabilities of interventional events. For example, assume we want the outcome to realize within a critical range. So, well, very low values of the outcome are bad, and very large, very high values of the outcome are also harmful. So we want the outcome to realize within a certain range of norm values. Then we can look at the probability of this event to happen given an intervention on the exposure. So that's the probability of the event that the outcome variable falls within the critical range had the treatment do X been uniformly applied to the population. And since the intervention distribution and its features refer to hypothetical experiments, they are causal quantities according to a certain scientific understanding of causality. And after setting up such a causal model, in the next step, maybe we want to quantify the causal relations that were depicted in the graph. And this can, for example, be done by quantitative methods and statistical modeling. Then we set up a statistical model which focuses on the joint distribution of observed variables. And this joint distribution can then be estimated based on the observational data, and it can be estimated non-parametrically in this most general setup. Or if you are willing to make further assumptions, it can also be estimated parametrically. And then the question is, what does the joint distribution of observed variables in a non-experimental context tell us about the outcome of a hypothetical experiment as described by the interventional distribution? We want to make this link, and this is what is called causal identification. And I will just skip very quickly over this slide. The original formulation of this graph-based framework was non-parametric, and we didn't have to make any assumptions about the functional forms, and we could still establish causal identification using graphical criteria such as the vector criterion, Fronter criterion, or even more general, we could use an algebraic machinery, an algorithmic identification procedure to establish causal identification, which is called do calculus. And the pros, of course, are that no additional assumptions are required with respect to the functional specifications. And contra would be, for example, at a later stage of the modeling process when we want to estimate these causal quantities, that non-parametric estimation with high dimensional data, especially if the variables are continuous, requires very large sample sizes. And if the variables are continuous, it even requires additional assumptions, some smoothing assumptions to avoid the curse of dimensionality. And another way that we are going to focus on in the remainder of this presentation, oh, sorry, that was too quick, is to assume parametric functional relationships, for example, linear relationships of the functional form. And, or maybe both, make assumptions about the distributional family of the unobserved variables. However, we should always start with the scientific theory, with a causal model. And a causal assumption that would justify the use of linear equations is the assumption of no effect moderation or of constant direct causal effects. That means that a direct causal effect, for example, of X on Y, is functionally independent of the values of the variables in the system. That is, direct causal effects are constant. So the effect of X on Y does not depend on the level of Z. or on the level of U of the unobserved confounder. It's just always the same, it's constant. And if we believe that this describes the data generating process, the causal mechanism, then we can use linear equations, linear structural equations. And here we replace this general functional notation using F with just linear equations. And what you can see here is that the U, the unobserved confounder, that is actually here in the bidirected edge, does not appear in the equations anymore, in linear equations. And that's also a convention. What happens instead of including U in these equations, we now allow for dependencies among the error terms for X and Y. So here we have a bidirected edge. We have an unobserved confounder. We assume an unobserved confounder for X and Y. And as a result, we model this using a covariance here in the for X and Y. Or more general, we allow the error term epsilon X and epsilon Y to be dependent, whereas we assume the other error terms, for example, for X and Z, where we assume no unobserved confounding, to still be independent. So, and if this causal model is true, this linear model, then this has implications for the joint distribution of observed variables. And in our situation, where we also assumed normality, maybe I didn't make this too explicit here, I didn't mention it here, we also assume a normal distribution. We don't have to, but for now, let's do it. And if that is the case, then the joint distribution of observed variables can be modeled with a covariance structure model. The joint distribution of X, Y, and Z is also normal, and it's parametrized by this finite dimensional vector of parameters, which contains the structural coefficients and the covariance entries of the error term distribution. This distribution, or this parameter vector theta, can be estimated given it's identified. And the statistical properties of estimators for covariance structure models are well understood. And there are many techniques to estimate these models. For example, maximum likelihood that requires normality, generalized least square, or for example, asymptotically distribution-free estimation does not require multivariate normality. Then we have also limited information estimators. For example, two-stage least squares could be applied. And there is a large body of literature on estimators for such models. And please ignore this hand icon here. That's part of a snapshot of screenshots I was taking. Okay, so we are still at the level of the modeling the joint distribution of observed variables. So we are still now in the statistical model. And we haven't answered or tackled the question of causal identification yet. So assume that we've estimated the joint distribution of our observed variables. This question is still open. What does this tell us about the interventional distribution? So we still need to link our causal quantities defined via the do operator to our statistical model. And to do this, we have introduced in our joint work, in my work together with Professor Volkle, we have introduced so-called causal effect functions. And causal effect functions, they map the parameters from the joint distribution of observed variables onto causal quantities. And these functions are labeled with G. So causal quantities denoted by small gamma can be represented as a function G of the parameters theta. And we call this function G causal effect functions. And this helps us to link the statistical model described by theta to our causal quantity described by gamma. And I will illustrate this causal effect function using this model where we have 3 successive measurements of blood insulin denoted by x1, x2, and x3, and 3 successive measurements of blood glucose denoted by y1, y2, y3. Here we assume that the measurement occasions are equally spaced over time. And I think Professor Völkle will tell you more about this assumption in his talk later. We assume mean-centered variables, which is a technical assumption just so that we don't have to model the mean structure. We simulated data based on a prior empirical study, and we use a standard deviation for the insulin levels of 11.48. So this number will pop up again later, so that you know that it's the population standard deviation of insulin. We have taken these values from the literature for healthy adults in the United States, and values below -40 on the mean-centered metric for blood glucose are considered hypoglycemia, and values above 80 are considered hyperglycemia. And both conditions should be avoided. So we have this critical range here from -40 to 80. And another assumption that we are making is that certain coefficients, so certain relations are constant over time. For example, here, the cross-leg effect of insulin on glucose is constant over time. This is an assumption that we are making. And in the empirical study that our data is based on, this delta t was, I think, 10 minutes. And I think it's rather a plausible assumption to think that these relations remain constant within a time interval of 10 minutes. But of course, it's an assumption, and it's always subject to debate. And we asked the question, what would the probability distribution of blood glucose at time 3 be had the treatment DO-X2 been uniformly applied to the population at time 2? So we want to know the behavior of Y3 given that we intervene on blood insulin levels at time 2. And we also want to know what's the optimal interventional level that we should choose at time 2 for insulin to maximize the probability for normal blood glucose levels at time 3. We assume a linear structural equation model. I think with looking at my watch, I'm not sure when I started. Was it 10 past? So
yes, it was 10 past. Yeah.
Okay, then I will not talk about this slide because this is just the linear model denoted in matrix notation. And I think most of you are familiar with linear structural equation models. So I will skip over this and show you the estimation results for this linear structural equation model. So we simulated 100 observations from a data generating process. The true values are in the first line, and we obtained estimates using the Lavam package in R for our structural coefficients, which you can see in the second line of the table. And the asymptotic standard errors are also reported. The model is identified, which we prove using a generalized version of Wall's rank rule. That's important. And now comes the link between this parameters theta to our causal quantities. So what we do now is we express our causal quantities defined by the dual operator here on the left-hand side of the equation as functions of the parameters in theta. So that's basically the causal effect functions here applied to our example. And we model the interventional mean as a causal effect function. We model the interventional variance. We model the entire density function, the entire interventional density function. and we model the probability that blood glucose levels realize within the critical range given the intervention. And on the right-hand side of these equations, you will always find the coefficients theta and no BU operator. So the BU operator only appears on the left-hand side, and it's linked to the parameter theta on the right-hand side. How do we estimate this causal quantity? That's pretty straightforward. We just replace the population values of the parameters on the right-hand side by the estimates. And by doing so, we obtain estimates of these causal quantities, which are depicted here. So we have the population values now in the fourth row, and the estimates and the asymptotic standard errors here in the first and second row. And here we can see that I included x here, the interventional level. So because the interventional mean is a function, a linear function of the interventional level. And to display the causal quantity gamma 3, which is the entire density function, I will use a graph because the density function is defined over a whole range of values. So what we do is we calculated point-wise estimates and point-wise asymptotic standard errors, which are plotted by the gray shaded area. The black curve is the point-wise estimate, and the dotted gray line is the true population density function. And similarly, we estimated the probability of treatment success. So the probability that glucose levels realized within the critical range, given an intervention on insulin at time 2. We plotted this function, we estimated this function for a whole range of interventional values, ranging from setting insulin level at time 2 to -50 up to +50. And we calculated the probability for treatment success for all these different interventional levels and came up with this curve. And also we have here an estimation error, which is denoted by the gray shaded area. And we can see that this curve has a unique maximum. So choosing on a means-centered metric, an insulin level of -38.3 maximizes the probability of treatment success. Okay, here's just a quick outlook, which is joint work with Professor Völkle and Professor West, Steve West from Arizona State University, where we have applied this method to cross-leg panel models with random intersets. So this method can be extended to more general panel data models. And looking at the time, I think I have to mention, and the slides will be made available, the testing of these assumptions, because these causal conclusions obviously are only reliable if our causal assumptions are true. And this can never be fully tested, but it can be partly tested. And those assumptions that cannot be tested should be analyzed using sensitivity analysis to see how wrong do our conclusions get if some of the untestable assumptions would be violated. But for now, I would finish this presentation by pointing to future research directions, which would be to apply this procedure, for example, to continuous time models, or apply this procedure to general cross-leg panel models. Professor Seifer will talk about these general cross-leg panel models later. So that's it from my side.